Okay, lecture 19. This is kind of a prep for the acid and base chapter where we do a lot of calculation. So this is going to be fast. There's not a lot to it, but for my class you'll have an exam over this, so it's really a lot of easy points, or it should be. So let's take a look. The first thing is you need to know the definitions of these terms, and then you need to be able to write the names and formulas of all the strong acids and strong bases. And I wasn't going to write these out and waste time doing that. Here are the formulas, here are the names. Should know them, but make sure that for the acids they end in acid. It's not nitric, it's nitric acid. For the bases, they all end in hydroxide. So lithium, sodium, and potassium are all group 1A elements. Calcium, strontium, and barium all group 2A elements. So there's a pattern there. But just make sure you know the 6 acids, 6 strong bases. What's the difference between a strong acid and base and a weak acid and base? Well, a strong acid when it goes into water, it reacts 100%. Or dissociates 100%. 100% dissociation. There's no HCl left. If you were Superman and you could look down and see individual atoms and ions in the water, you wouldn't find any HCl floating around. Only H3O plus and Cl minus, or like we used to do in 1170, H plus and Cl minus. For a weak acid like acetic acid, it goes into water, and we have to put in a double arrow in equilibrium because there is some shift back. It creates H3O plus like the other acid did, and the counter ion. But this is only about 5% at room temperature. I think it's like 4.7%, something like that, but a small amount. So, and same applies to strong bases. Strong bases dissociate 100%. They ionize 100%. A weak base only ionizes partially. So that's the difference between the two. Sure it's on there. Okay. Determine the conjugate pairs in the following acid-base reaction. Now before we do that, I want to go to the next problem here to talk about what a conjugate acid and base are. So determine the conjugate acid and conjugate base for each of the following. So if we have Br minus, and we consider that to be the base, then its conjugate acid is going to have H plus added to it. So for this one, we have the base and we have the conjugate acid. For water, if we consider water to be the base, then its conjugate acid is we just add H3O plus to it. But if we consider it to be, so base and conjugate acid, but if we consider water to be an acid, then its conjugate base is OH minus. So if we want to take whatever the species is, if we want to create its conjugate acid, add H plus to it, 1 H plus to it. If we want to make its conjugate base, take away an H plus. It has to be one hydrogen, and it has to be the positive charge. So you have to keep track of the charges. So for HCl, its conjugate acid we consider this the base, its conjugate acid would be H2Cl plus. Now that would be a very unusual thing, very unstable, but theoretically we can do it. If we want to make the conjugate acid of HCl, we add an H plus to it. If we want the conjugate base, take it away. So I think the rest of these we can do the same way. We have ammonia, conjugate acid. Now it becomes the ammonium ion by adding H plus to it. The conjugate base would be NH2 minus. Again, unstable compared to this thing, but possible. Conjugate acid of H3PO4, just add another H plus to it. Again, making something completely unstable, but that is what would be the conjugate acid of this guy. The conjugate base, take away 1 H+. So we have that. Don't take away all of them. Now see this H, these are the same. So now we see that by creating the conjugate base of phosphoric acid, we've created something that is still an acid, or can be considered an acid, or a base. We can add an H+ to it. So H2PO4-, the conjugate acid of it would be H3PO4, so we're back to what we started with up here. And the conjugate base would be, remove one more. For methane, to make the conjugate acid, this would be CH5+. Organic chemists would look at that and scream, but theoretically, we were just following the rules. We want to take a species and make its conjugate acid, add H+ to it. A conjugate base, take away an H+. Now, we'll go back to the Br-. I kind of skipped over this. Once you have this Br-, we can make the conjugate acid by adding H+ to it. So this is the conjugate acid. The conjugate base doesn't apply. A conjugate base means we have to take away an H+. So we can go to the conjugate acid, but trying to take Br- and making it into a conjugate base, we can't do it. We don't have any H+ left. So in the one direction, we can just keep adding H+ forever. Of course, after one or two of them, it just won't really be anything that would hold together realistically. But a conjugate base, once we've run out of once we've run out of hydrogens, we can no longer do anything further. We can't make the conjugate base of it. So whatever the species is, if they want you to make the conjugate acid, add an H+. Conjugate base, take away an H+. Now let's go back up here, and they want us to determine the conjugate pairs. So that's the acid and its conjugate base, or the base and its conjugate acid. In this case, we see that NH3 takes an H+, so this must be the base, according to our definitions. I'm not going to go into the definitions. I'll cover those in lectures. They're in the book. Those are the definitions you need to know. So it accepts an H+, so that's the base, so this must be its conjugate acid. And it makes sense because we have NH3, NH4+, there's an addition of H+, so that must be the conjugate acid. This is the acid, so this must be the conjugate base. I don't even have to look to determine, but we have water, loses H+, becomes OH-, so yes. So we have these pairs. How about the next one? Well, HCl, that's always an acid, but we can verify that. HCl loses its H+, so this is the conjugate base. Then water is the base, and it accepts an H+ from the HCl, so it becomes, or it turns into the conjugate acid. And you can see here that water acts as both an acid and a base. If it is up against a base, then it becomes an acid. If it's up against an acid, it becomes a base. So water is very flexible in that regard. Now we have water here again. We don't know what it does yet. We have H2PO4-, and water becomes H3O+, so it's acting as a base here, which means this must be an acid. They always work in that fashion. And then conjugate acid, so this must be conjugate base. So there's always an acid, always a base on the left side. The conjugate acid and conjugate base are on the other side, and so all four must be accounted for, and there's always going to be two on each side. So that's all we need to do there. Now, why is water considered amphiprotic or amphoteric? It acts as an acid and a base. So, and we just saw that. Actually, I can put it right here. The reason it acts, it's considered that is because under the right conditions, it'll act as an acid. Under different conditions, it'll act as a base. So we can get water can change into H3O+. If it's acting as a base, it's conjugate acid. And then water, it can act as an acid and change into OH-, so it has its conjugate base. Water has that property, and that's one of the several things about water that make it fairly unique and very useful, and we use that, its ability to do that, quite a bit in acid-base chemistry. Name a species that is a Lewis acid, but not a Bronsted-Lowry, that's what Bl is, or Arrhenius acid. So a Lewis acid is a species that can form a covalent bond by accepting an electron pair. So we have something like silver ion plus, what do we want here, like ammonia with a lone pair, can go to what we call a coordinate covalent complex. It forms a coordinate covalent bond, so this is a coordination complex. Now, this is the Lewis acid, and so this would be a Lewis base. We'll see this more in a later chapter, but it accepts a lone pair, creating this coordinate covalent bond. Now, this is not a Arrhenius acid. There's no H plus present, or Bronsted-Lowry acid either. It doesn't have the same, well, it doesn't have the H plus. It doesn't have that, what we consider normally something that an acid has to have. So this is just a bare silver ion that's completely different, and it's what it is, it's a very general definition of an acid. So an Arrhenius acid is also a Bronsted-Lowry acid, is also a Lewis acid, but it doesn't work in the opposite direction. A Lewis acid does not have to be a Bronsted-Lowry or Arrhenius acid. So it's a very special case. It seems like we just pulled that out of nowhere, and it's kind of silly, but it turns out to be the basis for a very large portion of chemistry, of inorganic chemistry. So it's important to know.